So for 17, what was given to you was a point 9, -5, and the slope of -1/3. So you have to use point slope to find the slope intercept. So you plug in y minus -5, which changes to y plus 5, is equal to -1/3, and then x minus 9. So when you distribute the -1/3, you get y plus 5 is equal to -1/3 x plus 3. And then you have to subtract the 5 from each side to get y by itself. So then you get y equals -1/3 x minus 2.
So that's point slope form. They give you a point slope with that information in.
Okay, so I did 23. You're just supposed to find the perpendicular line to y equals 1/3 x plus 3 with the point 4, 1. So since it's perpendicular, you have to find the opposite reciprocal. So the opposite reciprocal of 1/3 would be -3. So, and then you would do point slope, so that would be y minus 1 equals -3 x, or times x minus 4. And then that would go, if you like multiply that, you get -3 x plus 12, and then you get y equals -3 x plus 13.
Any questions for Nina with perpendicular? Nice job, Nina. You got it. And last problem, 29, had some fractions in it. Make sure you're keeping those fractions in the problem. Don't write it as a mixed number, keep it as a complex fraction. The 19/4, don't have it as 4 and 1/4 or 4 3/4. When you check your answers in the back of the book, you'll see that they are written in complex fraction form as well. You won't see them written as mixed numbers. So today we are going to just do a small bit of notes, just a page. Still talking about the equation of a line, but we're going to talk about a special line called a direct variation line. Your homework I have is a worksheet. It's 2 separate worksheets. I kind of picked a couple of problems from the worksheets. Tomorrow you have a quiz. And the quiz is on sections 2.1 through 2.4. But there isn't an actual review worksheet for the quiz. So the homework I have for the night kind of like a review because it's still asking you to calculate, still find the equation of a line, think about parallel perpendicular. But the homework does not review section 2.1. And section 2.1 was when we talked about that function notation, f of x, evaluating a function, y is a function. So you want to make sure that you do look over sections like say 2.1 and 2.2, and review those concepts, just kind of glancing at the notes and looking over your homework. But 2.4 covers slope, covers writing equations of lines, so that kind of covers 2.3 and 2.4. So no formal review for your quiz tomorrow. I will be able to answer a question or two prior to the quiz tomorrow. Once we start taking tests, the test will be entire 40-minute allotment tests. So when we get to that point, we won't really be answering questions prior to you taking tests. So in your notes at the top, it should say direct variation. We talked about writing the equation of a line yesterday when you have parallel and perpendicular lines, similar to the one that Nina did. When you have an ordered pair and a slope, and we can use that point slope form. So we're going to talk about a special equation today, still a line, but it's a special type of line, and that line is called a direct variation. So a direct variation, you're going to see the words when y varies directly with x. This is still a line, but this line always goes through the origin. So y varies directly with x is still a line. But this special line doesn't have a y-intercept. It has a consistent slope. It always goes through the origin, so it has no y-intercept. The equation of a direct variation is y equals a times x. So we just have a y and an x. That's why we get that y varies directly with x. So whatever x does, that forces y to follow. The variation constant is the a value. And we kind of refer to that as the slope because it increases at a constant rate. So because it's a different type of equation, I can't use an m to represent slope. You'll see in the kind of functions that we work with, it's a new equation, generally it gets different letters. So y equals mx plus b is slope-intercept form, where m is the slope. Since this is a special equation, a direct variation, the slope is an a. And that a represents the variation constant, which is another way of saying the slope, the rate at which the graph rises or falls. So in example 6, it wants us to decide if the data in the table shows a direct variation. And then it says, if so, write an equation relating x and y. There are two different ways we can do this. The first way we can do it is, obviously, got a little graph over here, is by graphing. And then seeing if the graph rises or falls at the same rate. So that's one way. Bless you. So we're going to kind of treat this as a set of points. We're going to plot our points. Does the slope rise or fall at the same rate? The other way we're going to do it is algebraically, by actually calculating a. And if that a is constant, then it also is a direct variation. Which is essentially what you're doing with the graph. If it's rising or falling at the same rate, the slope is constant. it's the same from one point to the next. So we're going to do the graphing part first, and then we'll do the algebra part to support the graph. So both of them could be ways to show that a table of values would be a direct variation. We got to do something to kind of prove your answer being a yes or a no. So the table of values, x and y, it's like having a t-chart, but it's going left and right. So plot those pair of points, there are 5 of them. You probably can make your graph go a little further. Mine's at the edge of its screen. So after you plot your points, in order to find the slope, you're looking to see from one point to the next, is it the same rate? So remember, slope is rise over run. So from my first point, I'm going down 1 over 3. The second one is down 1 over 3. My third one is down 1 over 3. To get to my last point, I would move down 1 over 3. So this is a constant rate. If I continue going the other way, if I go up 1 and backwards 3, that's where I would hit the origin. And that's what I need to do. I need to make sure that I hit the origin, and then it's also falling or rising at a constant rate. So I could continue that and go the other direction. Because it's rising or falling at the same rate. That's our A value. So whatever the slope is from one point to the next, as long as it's the same, and the graph goes through the origin, then we say that it's a direct variation. So my A is 1/3. It says to write an equation. My equation would just be then 1/3 x. Yes. Negative, yeah, thank you. Yes. Negative 1/3 since it's going down. So must go through the origin, and the rate from one point to the next must be the same for every set of points. So from one point to the next, it has to be continual, it has to be the same or constant. So that's the graphing application by looking at the graph. If you go over here, we're going to see if we can show this algebraically by just calculating the slope. So the equation is y equals ax. But if I want to find the slope, what are you doing to calculate the slope? And the slope is the a value. So how would I calculate a, Chris? In this equation, though, we don't even need to do that. So how can I solve this equation for a? Peter? Right, we can plug in 3 and -1. So we could plug in a 3 and a -1. And then Peter, to solve for a, you would divide by 3. So a would be equal to -1/3. To find a, in general, Chris was giving me the regular formula for a slope, y equals mx plus b. But for this, to find a, Michael, are you stretching or raising your hand? Okay, so for this to find a, you just need to take y and divide it by x. So if you take your pair of points and just take the y divided by x value, because it's a direct variation, you don't need to do the whole slope formula. So you're just comparing the ratio of your y divided by x. That's actually the slope of a direct variation. If that's the same for every pair of numbers, then it is a direct variation. So I'm just going to do my work above the little chart here. So we already said this is -1 divided by 3. If I take y divided by x, I have -2 divided by 6, which is also -1 divided by 3. That needs to be the same for every pair of values. If it is the same, then it's constant, and it's a direct variation. So again, looking at my y divided by x, 3 divided by -9 is -1/3. y divided by x, negative 4 divided by 12 is negative 1/3, and finally y divided by x, I'd get a negative 1/3. So you're looking at each pair of values and kind of proving or showing that they create the same value every time. And if that is the case, then my a value is constant, and I could use that a value to write the equation. Y equals negative 1/3 times x. So direct variation is still a line. It's a line that goes through the origin, and it has a consistent rate of change. It's changing at the same rate from one point to the next. Questions? So looking at the next set of examples, it wants you to decide if the equation represents a direct variation. So this is just a yes or no. Make sure you kind of have like a reason as to why you're saying yes or no. But a direct variation should be of the form y equals a times x. So Leah, is the first one a direct variation? Yeah, because it's in the same exact format. You have an 8, which is your slope. You have a y and an x. How about letter B? Jack.
Yes.
Why?
Because that's the same thing as y equals 1/8.
It's the same thing as
Y equals 1/8.
not quite. Where's the x in this problem? On the bottom. So if I separated, this would be an 8 and then times 1 over x. Jack, I think you're saying x over 8,
Oh.
which is what that's what I think you were meaning, correct?
Yeah.
So because the x is on the bottom here and not the numerical value on the bottom, this is not a direct variation. So this is really saying you have 8 times 1 over x. 1 over x is actually called an inverse variation. You're doing the opposite instead of multiplying. So this here, Jack, would be a direct variation, but this one is not. How about the last one, letter C, Peter? Why not? Yeah, it doesn't go through the origin. It has a b value of 1. A direct variation goes directly through the origin. It doesn't have a b. It doesn't have a y-intercept. So yes, it still has a slope, but it always goes through the origin. So a direct variation is a specific type of line. It's a line that only goes through the origin. It still has a slope, rises or falls at the same rate, but it's always going through the origin. There's one other little question down at the bottom. As I said, a short day of notes here. And this is talking a little bit about physics. You don't need to know physics, but we sometimes relate to some of the rules and properties and laws in physics. So Hooke's law states that the distance d in inches of a spring, how far it stretches, varies directly with the force that is applied to it. Does anybody have a slinky? Know what a slinky is? Do we know what a slinky is? Okay, good. So that slinky is like a coil. They now make them plastic, but I'm old. Oh, I had one that was like heavy duty metal, and your parents probably had one that was heavy duty metal. Josh is like, yeah, you are old, because he's laughing at me. I know, how dare him? Or you're just agreeing with me. You know that heavy duty metal one, right? No, he's saying I'm old. It's okay. So think of that slinky. The goal of the slinky is to like flip down the stairs. But also you can stretch it. And our slinkies always end up broken. Because they get like all twisted. I don't know what the girls do. It's Sadie. Sorry, Sadie. She's the one that always gets her slinky twisted. And then you try and untwist it and it never works right again. So think of this slinky here, and it really is a spring. And the further you pull this spring, obviously the further it stretches. But when you're pulling on something, that's called force. So anytime you're applying pressure to something to pull it apart, you're actually applying force. To open the lid on your Gatorade bottle, you're applying force to open that lid. So this is saying if I apply a lot of force, my spring should stretch further.
If I don't apply a lot of force, it's not going to stretch as far. So suppose we have a spring that we can stretch 15 inches, a little more than a foot, and we're applying a force of 9 pounds to get it to stretch 15 inches. It says write an equation that relates distance to force. Which one of those would be our independent variable? Jack? Force, because force is going to make the spring stretch more. So the more force, the further the string stretches. If I can speak here. So the distance would be related to some kind of slope or constant value times the force that I apply to it. So when we're trying to write an equation with direct variation, we have an y value and an x value, but there's no b. So this is going to be a direct variation that goes directly through the origin. How would you come up with an equation that relates the information that we're given? Peter.
15.
Yeah, so it says the spring is stretching a distance of 15 inches. The force is 9 pounds. So I have an x and a y, or a d and an f that we can plug into our equation. So distance, trying to figure out that a value, what is the constant that would be applied to this equation? And then we're plugging in the 9. And if you divide by 9, it is 15/9 reduced. 5 thirds. So that's our constant. That's called the variation constant. If I was graphing this, I'd go up 5 over 3, up 5 over 3. Our equation then would be distance is equal to 5 thirds times the force. So that's based off of this Hooke's law. So if I take 5 thirds times the force, I should be able to figure out how far I can stretch a spring. Part B says use the equation, so we're going to use the equation we just calculated, to find the distance the spring would stretch if I applied a force of 6 pounds to it. So now that I know what that constant is, we have the equation. We want to find the distance a spring could be stretched if I use 6 pounds of force. So JT 5 thirds times 6 is? 10. And what's that 10 if we're talking about distance? Inches. So when you're writing the equation with a direct variation, you have to kind of think what's the independent variable. That's going to be where x is usually located. What's your dependent variable? That'll let you know where to place those variables. So like independent, that's the one that forces or controls the other variable. So in this case, literally the force is the part that's controlling the distance. Questions? So I have a worksheet. The problems are on the board. So when you get the worksheet, make sure you're writing the problems at the top of the page. And I will put the answers to this on Google Classroom and I will also send it through Remember. Please write these on a separate piece of paper. I will collect this from you tomorrow. So again, section 2-4. 1 through 7 odd, that's working on, you're given 2 ordered pairs, coming up with the equation of a line by finding the slope and the y-intercept. 17 to 23 odd, that goes over, again, trying to write an equation of a line, but that asks you to write the equation of a line in standard form instead of slope-intercept form. 25 to 27 is a little word problem, they all go together. And then when you flip it over, the other side of the page is talking about the direct variation. So 5 to 11 odd, you're given an x and a y, write the equation for direct variation, and then 13 to 20. So 13, 18 would be deciding if it is in direct variation form. 19 and 20, those two problems there are the little charts. Say again? I'm gonna, yeah, I'm gonna give it out right now. So grab a partner, you have 12 minutes to get a head start on this. Again, tonight, make sure you look through your notes, kind of refresh yourself, the 2-1, sections 2-1 and 2-2. Mm-hmm.
So for mine's group, we have to like plug it in. Is it okay if I just do this?
Yes, yeah.
Okay.
Yeah.
Is that like
Either
the same
way,
thing?
yes, exactly the
So
same
on the
thing.
test, can I do it?
Yes, and it's more personal preference.
Yeah.
So which equation form do you prefer? Correct. Okay, so what kind of line would you underline? Okay, so vertical. And when you say vertical line, there's no line that says. Pick an X number. Same two. Yeah, so that's really. Mhm.